Huh? All right, so we get back to the lab activity on Tuesday. OBS is recording already, so if you have any questions, now is a good time to ask. So we'll start with this one, and I'm going to take the test myself just to make sure that my answers are consistent with what Canvas thinks is correct. And of course, what Canvas thinks is correct is programmed by me, so I can be consistently wrong and not be detectable. That's the problem of having developers or the programmers to also test whatever they are developing. Because if they knew that the logic was wrong in the first place, they would have written it in a different way. So they're going to test the program or the software based on the same assumption when they write the program, which means they're most likely going to miss a lot of things. And that's why you cannot have developers to test their own programs. Okay, so this is question number 1. This is the test. I'm actually taking the test myself. So in this particular question, the question is asking about this p. How can what is the maximum p as an integer so that, for a particular given binary number, x, I want the product of x and 2 to the power of p plus 5 to be just less than or equal to 2 to the power of 64 minus 1, which turns out to be the largest value you can represent using a 64-bit unsigned integer. Okay, so the relevancy of this question to the floating point number calculation is basically asking how much can I push the value of a binary number before I divide it by 10? Because division by 10 is most likely going to be lossy, which means I'm going to lose some precision. And in order to minimize the loss of precision or the amount of error, I want the numerator or the dividend to be as large as possible. Okay, and I can make numbers big really easily. I can just keep left shifting the number, which is basically the same thing as incrementing p by 1. Every time I left shift, I'm making p 1 bigger than before. So the question is, how far can I push it? So to answer this question, you can either write a program, a short program to do it, or you can use the math to solve this problem. So let me show you how to use the math way to solve this problem. Okay. I know you cannot see my tablet yet because I'm not there yet. So 310, this is Tuesday, Thursday. And restart advisor. Okay, there we go. All right, so the first part is basically just algebra. Okay, so we want to solve this problem using algebra. And let me go back to the question itself. Okay, so I'll give you the general solution, regardless of what x is. So x times 2 to the power of p plus 5, the whole thing has to be less than or equal to 2 to the power of 64 minus 1. Okay, so now we switch back to the tablet and you can see the problem. Okay, so the first thing we do is we take the log of both sides. Most of the time, if what you need to solve for is a power of something, it's going to involve log, okay? But I just lied because I don't want to do log just yet, because the plus 5 is kind of ickish, to be there. So what we want to do is to put all the constants to one side before we take the log. So now we look at this equation, or inequality, and then we say, well, it's the same thing as x times 2 to the power of p is being less than or equal to 2 to the power of 64 minus 1 minus 5. In other words, I'm just subtracting 5 from both sides. Is that okay? So this way, the left-hand side looks clean. And now we can take the log. So we say the log of x times 2 to the power of p has to be less than or equal to the log of 2 to the power of 64 minus 6. I'm just combining the minus 5 minus 1 to minus 6. Is that okay? All right. And then we say this is log of x plus the log of 2 to the power of p, because when you look at the log of a product, it is the same as the sum of the individual components of the multiplication. Is that okay? All right. So, so now we take the p out, because when you look at the exponent of a component inside a log, the exponent can be separated out, just like that. Is that okay? So now we get all the components that we need, because now we can just say that p is less than or equal to the log of 2 to the power of 64 minus 6 minus the log of x, and then the whole thing divided by the log of 2. Now, for those of you who understand what is the log 2 of something, you can remove all mentioning of log 2 and just change all the log to log 2 of something. If you don't know what I'm talking about, just keep it this way. But this is it, okay? This is the answer. If this side is giving you something that is not an integer, how do you make sure that p is less than or equal to that thing that is not an integer? P has to be an integer. But the other side, this side here, may not be an integer. So how do you turn it into an integer so that p is always less than or equal to this particular quantity? Yep, we just stick the floor. Very good. Okay, so the actual answer is p equals to the log, the floor of the log of 2 to the power of 64 minus 6 minus the log of x, and then the whole thing divided by the log of 2. Is that okay? All right, so we'll take a look at the actual question itself. So in this particular question, x is 720271. 72071. I'm going to copy it to the tablet, and then I'll do the calculation, and then I'll put the answer in so that we can check whether that is actually correct or not. So in this case, we have x equaling to 720271. Okay, there we go. And I'm going to do the calculation myself. So 2 to the power of 64 minus 6. Take the log of that. And then we have the number itself, 720271. Take the log of that. Do the subtraction. Take the log of 2. Do the division. So I got 44 for this particular question. Are you guys getting 44? For this one? I'm not too worried. 44? It should be 44.5 something, but when you take the floor of that, it becomes just 44. All right, so are we okay with the math? Are we okay with how this connects to floating point representation? Are there any issues or questions about this? Yep.
So this will be on the test too, right?
Since we did say that there won't be any floating point stuff in the test, so this will not be in the test. Well, not in exam 1, it'll be in the next one. Okay, next question. So question number 2 is actually a lot easier than most people think it is. It really is just asking, in this case, what is the rounded version of 1.532 and what is the truncated version of 1.532. The rounded version is 2 because 1.5 something has the fractional part being at least 0.5, so you round up. But the truncated version is just getting rid of the portion that is not the whole portion, so you just get 1 left. So now you have 2 minus 1, and it's just 1. So then why do I put in all of this confusion stuff? Because I want to relate this to the floating point calculation stuff. Now the floating point conversion, okay, from base 10 to base 2, if I can use log and exponent and stuff like that, it can be done pretty quickly. But then it becomes a chicken and egg problem, doesn't it? So I want to use only integer arithmetic to get it done. So if I want, this is one way to look at round. Okay, when you take the round, or when you round a number value x, it is the same thing as adding 1/2 to x and then take the floor. This works for any x. Okay, and you can rewrite it as 2x plus 1, the whole thing divided by 2. Okay, no big deal. But this also means that x itself cannot be an integer, because we want to avoid the use of double and float in the whole conversion process. So I cannot use round like this. But we also remember that every time we use round, it is after a division by 10. Okay? So that means the only case we encounter rounding is when we deal with this, when we are rounding the result of some number, some integer divided by 10. Is that okay? So when you plug in x divided by 10 into x here, then we have x divided by 10 as one fraction plus 1 divided by 2. And then you can use algebra to figure this out and go like, oh, it really is the same thing as x plus 5 and then the whole thing divided by 10, and then we take the floor of that. Remember, x is an integer. So if x is an integer, x plus 5 is also an integer. An integer divided by 10, which is an integer, can use just integer division, which automatically does the truncation, or the floor. So that means now we have a way to do the rounding, but without using any double or float operations. So that is why I included this part here. It is not to confuse you. It is only here to help you connect this particular exercise to the discussion of floating point number conversion. Yep.
So for the truncated part, what number do you plug in for x? It's like around x divided by 10. Equal 15 or 15.32? You said integers, so I assume it's 15.
It's 1.532.
Oh, okay.
It's not 15, it is 1.532 because we are rounding the result of 15.32 divided by 10.
No, he's saying what would the x be if you wanted to use that formula?
Oh, you mean this one?
Yeah.
If you're using this one, then x is 15.32. If you're using this one, then x is 1.532. Because the question is asking about the rounded version of the entire division and not just 15.32. Hello. Ah, okay. Okay, moving on to the next question. So the next two questions are also related. They're basically flip sides of each other. Question number 3. So question number 3 is, okay, so let's read the first part first. The main idea from converting from base 10 scientific notation to base 2 scientific notation is to change the unit from some kind of power of 10, some power of 10 to some power of 2. That really is the whole idea of conversion, from converting from base 10 scientific notation to base 2 scientific notation. Is we are changing the unit. That's all we're doing. So that's why this question is trying to make it, simplify the concept. This is a particular quantity or particular value, 1.45 times 10 to the power of -5. So if I know ahead of time, don't ask me why, but magically if I know ahead of time, then my precision is only all the way down to 2 to the power of -20. Then the question is, how do I express the value of 1.45 times 10 to the power of -5 in units of 2 to the power of -20? So to figure that out, to figure out why it is 15, you just do a division. There are 15, approximately 15, 2 to the power of -20 in 1.45 times 10 to the power of -5. So it's really just a division. But then in the following part, instead of just writing it's 15 times 2 to the power of negative 20, I convert the 15 to 1111 in base 2. Is that okay? 15 in base 10 is the same thing as 1111 in base 2, because 15 is 1 plus 2 plus 4 plus 8. Okay? But now that the base of the mantissa is the same as the base of the exponent, I can now shift the point easily. So I can shift the implicit point, which is here, to the right-hand side of the least significant digit. If I shift it to the left 3 times, then I end up with 1.111. But every time I shift one place to the left-hand side, every time I shift the binary point to the left-hand side, I am actually dividing the mantissa by 2, which is changing the value that it is representing. That's not okay. So in order to counter that halving, I have to increment the exponent of 2 by 1 every time I shift the binary point. So that's why when it was, in the beginning, it was negative 20, I have to increment it 3 times, so it becomes negative 17. Yep?
Why do you want to bring it back
Bring what back?
to 17 instead of 20? I mean,
Well, this is what the double precision.
why are you doing the whole thing in the first place?
Why do we do what whole thing in the first place?
Question 3.
Question 3.
Like,
This okay. How is this part connecting to the whole discussion of double precision floating point numbers? It's the concept. Is it relating to the floating point number discussion? Because once we know the fractional part of the mantissa and it's normalized, and we know what power of 2 we have to multiply it to, now we know how to represent it as a double. Because now we have 111 and then all zeros as a fractional part of the mantissa, and then we also have a negative 17 plus 1023 as E. So now we know exactly how to use the zeros and ones in a double precision floating point number. So the question itself, okay, the actual question that you have to answer is really just to figure out, okay, if the quantity that you're given with is, in this case, 1.146 times 10 to the power of negative 5, if I only let you express this value, but in units of 2 to the power of negative 22, how many 2 to the power of negative 22 do we have to specify that value? It's just a division. But you have to round after the division. So in this case, actually, let me see if I have that application installed here. Let me see if I have the calculator app. Nope, not here. Okay. Because that way you can actually see how I use the calculator. Okay, so let me do this calculation. 1.146 times 10 to the power of negative 5. Okay, by observing some people doing this on Tuesday, and also yesterday because of the Wednesday lab is 1 day behind you guys, you might want to learn how to use a calculator. Because the E button on the calculator is the natural log constant to the power of something. It is not to specify the exponent of a scientific notation. Okay, I saw that several people did it. Okay, and they go like, no, that may not be the key that you're looking into. Okay. Okay, so this is the number. We are dividing it by 2 to the power of negative 22. So to specify a negative power, you also have to find the key that flips the sign of a number. Okay, I just punched something correctly. 1.146 times 10 to the power of negative 5. And we have 2, 22, division. So I'm getting 48 over here. There we go.
About 40.
Hmm?
About 48.
Yep, 48.0 something, so it's really close to 48. All right, the next question. The next question is really the flip side of this. Okay, question number 3 is asking you about the quantity, but it is fixing the unit. The next question is asking you about the unit, and it doesn't really care about the quantity. Yep.
I think what got me confused with number 3 and 4 is the fact that you used x to mean different things.
That is correct.
That's why I was like, why is there an x?
Well, x is just a variable, right? I mean, you can reuse x
Oh, yeah.
and y and whatever
You
in.
told me they're the same thing. I was like, oh, x represents that same number that I'm supposed to find. It was just, I used the same variable to mean the same thing for both numbers, which made
I see. Can I count that as having a strong sense of how things ought to be? Okay, so this question is actually the reverse of that. So with this question, there are several restrictions. So in this question, I want to express, okay, where is the general? Okay, so this really summarizes the entire thing in this question. So some kind of value, v, okay, has to be expressed as some kind of quantity x times some kind of unit of 2 to the power of something. But the extra requirement is x itself has to be between 2 to the power of 52 and 2 to the power of 53 minus 1. So now you have to ask the question, if x is has to be between these two quantities, what is that going to do? How is that going to help you answer the question? Because you have two unknowns, right? If you look at this thing here, ignoring this part, you have two unknowns. X is an unknown, P is an unknown. You cannot resolve two unknowns at the same time with only one single equation. There's no way you can do it. But the second part of the conjunction is giving you enough constraints to solve this problem. Okay? So let me just repeat that on the tablet, and then we'll solve the question, or solve for this P here. Okay. And then, okay, so that should be sufficient. There we go. So this is the bottom line, okay? Not re-mentioning the restriction on x. This is the bottom line. So if you look at this one here, then you go like, okay, we need to solve for P. How do we do that? Well, first of all, we take the log of both sides. Okay, not a problem. And then we separate the part that has the P out. So we have log x plus P times log 2. So I'm actually combining a few steps into one, but it should look familiar, okay? Is that okay? All right. So now I can actually know what P is, okay? So I can express P in everything else. That's the better way to put it. So P is the log of V divided by the log of 2 minus the log of x divided by the log of 2. Right? But we still have two unknowns. So we have to somehow get rid of one of the unknowns. So what do you think we should do now? I can't really do much about what this is now known to be a particular quantity. But I don't know about this one. Well, or do we? So let's focus on log x divided by log 2. Okay, let's focus on this term here. What do you think that is actually telling us? Yep.
So x is between, since x is between two numbers, if we took the log of it, we'd probably get close to a power.
Okay, let's look at it this way. We know the minimum value of x, don't we? We know the maximum number of x, right? So let's plug in those things in and see if we can get some clues out of this, okay? Yep.
Wouldn't it be easier just to use the clue of the x restriction, saying that x must use 53 bits?
Yes. But I want to show you how the math works out to show that as well.
Okay.
Okay, so this is the minimum, okay? That's a poorly written 5. There we go. So this is the minimum. X cannot be less than this, right? So if this is as small as x can get, what is this value? Oh, come on, you guys know. 52, very good. Okay, so this is just 52. And let's take a look at the other one. The log of 2 to the power of 53 minus 1, the whole thing divided by the log of 2. And what do you think that boils down to? Now, we know one thing, don't we? We know that if it's not for this bothersome minus 1, then the answer would have been 53.
Still.
So in this case, we know it is going to be just a little bit less than 53. Okay? But can we do something like this? Okay, cool. But the other one is the same way too, isn't it? I can put a floor in here and it doesn't change anything. Because 52 and the floor of 52 are exactly the same thing. So that tells us something, because now we can put this back here and say that, oh, this is really just 52. All we really care is what is the bit position of the most significant bit of x. That is all that we care. We don't need to know what x is, we just need to know what is the bit position of the most significant bit of x. So now we actually can solve the problem, because the other number is just the log of v, which is given to you, divided by the log of 2. Okay, so that's something that we already know. So now we can just do the calculation. So let me go back to the question, and we are supposed to convert let me write it down first. So v is 9.515 times 10 to the power of 28. So let's do the calculation. So 9.515 times 10 to the power of 28. Take the log of that. Take the log of 2. Do the division. So I get 96. 96 minus 52 is 44. So this is my answer, 44. So the bottom line is, if these are the restrictions and this is the quantity that I need to specify, then basically the quantity, the value itself, is expressed in units of 2 to the power of 44. There's no way we can actually resolve any quantity that is less than 2 to the power of 44. Everything that is below that is lost. There's no precision below that. Which is kind of profound, because this is telling us that if you try to add any value that is less than 2 to the power of 44 to this particular number, it disappears. And 2 to the power of 44 is not a very small number either. It is about, it's about 16, what is the one after the trillion?
Quadrillion.
Quadrillion? Okay, so it's about 16 quadrillion. So you can add 16 quadrillion to this particular value, and it is the same thing as adding 0 to it, because it is below the unit that we are using to specify the quantity. Okay, you guys don't seem to think that is important.
Can you say that one more time?
Huh?
Can you say that one more time?
Okay. So the answer to this question is basically saying it's basically saying E, which is 9.515 times 10 to the power of 28. If you use the double precision floating point format, it boils down to the smallest quantity that you can add to actually make a difference to this particular value is 2 to the power of 44. If you try to add any quantity that is less than 2 to the power of 44, it's just 0.
Makes sense.
And that is kind of important because if you actually need to add these types of values, you have to be aware of when it just goes away, disappears. Now, if you do add like 2 to the power of 44 or 45, it has a very small impact to this particular value. So you're basically just adding 1 or 2 to this particular quantity to x.
Yeah.
And that basically is telling you that when you're adding two double precision floating point numbers and the magnitude of the numbers are vastly different, you the result may not be actually any different from before. Now, multiplication is different, but for addition and subtraction, if the magnitudes are very different, doubles basically you can end up like doing nothing to the values.
Is that why it's common that when you see like in a if statement when somebody's trying to compare two numbers to see if they're equal, two doubles, they'll do like one number minus a number less than or equal to like a really, really small number?
Because you have to look for the epsilon. The epsilon is due to the quantization of values that you're storing in a double. But what quantum you're going to use has to do with the value itself. So when you're comparing two values and you're saying, okay, should I consider these the same? The quantum or the difference that you should use to consider those things being the same has to do with the value of the things that you're comparing. And it's the same kind of calculation. So that is significant in a very interesting way because if you are a scientist and you're running particle simulation or something that involves maths with a huge difference of magnitude, then you can encounter these problems and it won't even show up until much later. And a lot of times by rearranging in algebra, by rearranging the priority and when you do a particular addition and when you do the actual multiplication, you can avoid some of these problems. So that means what seems to be the same expression to mathematician, to a computer scientist, it can be different because it can give you completely different results. So in this class, we're not going to get too deep into that stuff because I think we only allocated like 2 hours to talk about floating point representation, and I think we have spent like maybe 4 hours already on double precision floating point numbers. But eventually, this will become useful. It will become relevant. Okay, so I'm just going to answer 4 questions in the quiz because the other 4 are basically identical. So I'm going to turn it in, and hopefully I get 50% of the points. All right, let's see. 1 out of 1. Yay. 1, 2, 3, 4. Okay, I got all of them. As I said, if I make a mistake, I would have made the same mistake twice. So I will be self-consistent. Okay, so this is only one part of the lab. There's another part too. So the second part of the lab is me finishing up the 3x3 carry look ahead adder. Okay, it's almost done, but it's not quite done. I started this with the first lab, so I'm going to finish it with the second lab. Okay, so let me get rid of all the extra stuff that I don't really need, and then I'll see if you guys have any questions about the current design and then before we move on. Yep.
Quick question. Is your version going to be similar to the one that we had for labs when we were building? Is it going to be almost the same?
It's almost the same, except I may not have the same number of tunnels, or the positions would be different. Okay. But in terms of the construct and the architecture, it will be the same.
Okay.
Yep. Okay, so the overall design of the 3x3 carry look ahead adder slash 3x3 borrow look ahead subtractor is going to be the same. The only difference between this one and the one that you had to deal with earlier is this one has the unification circuit already. The unification circuit has an extra input pin which we just call A in the expression in class, but in here I call it as A/S because A is adding, S is subtracting, and the slash means the negation of S. So the slash means when this signal is 0, it specifies subtraction. That's basically the convention. So when you look at this pin, it's a single bit pin, because I just need one single bit to specify, are we adding or are we subtracting? So what we do here is we use this thing here to feed the same bit into a 3-input splitter. So this way, I'm basically generating a 3-bit wire where every single bit is the same. I'm just making copies of that one single bit. But this is necessary in order to feed this wire into a multi-bit gate, which is doing what the function S is doing in class. This is what we were talking about in class. It is a negated exclusive OR gate. So whatever is coming out of this thing, this wire, is going into the circuit to calculate the G terms, and also going into the circuit to calculate all the P terms. So this way, by negating or by specifying one single bit, I can now say, okay, the G and the P terms are now for subtraction, or they're for addition. Is that okay? All right. So we're almost done, okay, because I just, I took care of the most complicated of all the carry bits, which is K3. But the nice part about this particular design is this circuit does not need to change at all. Whether I'm adding or subtracting, it stays the same. If you did the lab the same way as as we talked about, your design would also be the same thing, because your K3 circuit would be independent to whether we are adding or subtracting, because it only relies on the G and the P terms. It does not rely on the X or the Y term. Is that okay? Mm-hmm. And this is why I want your K3, K2, and K1 circuits to only make use of the P and the G terms and not the X or the Y terms. Because this way, we fix one place to redefine the G and the P, and now we can do addition or subtraction. So the only thing left to do is to finish up K2 and K1. So let's do K2 this time. And I think I have the notes opened somewhere. Yep, so this will be the one. So K2 is G1 plus P1 G0. Okay, so I'm going to make the general construct first. So the general construct, I can just copy and paste a lot of that from here. So I'm going to, in fact, I'm just going to be super lazy here and just copy the whole thing. And then we just get rid of the stuff that we don't need. I'll keep the gates, okay, and I can change the gates later, but I'm just going to remove the wirings. There we go. And change a few things, because when you look at this equation, K2, it only has 2 AND gates, one with 2 input and one with 3 input. So the one that has 4 input is not needed anymore. And then we just have to wire things correctly. G1 goes straight to the OR gate. So G1 is going straight to the OR gate, like that. And then the OR gate only has 3 inputs, so that is the other thing that we have to adjust. And of course, it doesn't rewire things accordingly. So this one is technically gone. This one goes down. I know it looks ugly. Okay, P1G0 is the 2 input AND gate. So P1 and G0. So G0 and P1. And then the 3 input one has K0, P0, P1. So we got K0 and then P0, P1. Cool. And of course, the name of the output pins should change accordingly as well. This is K2. There we go. Now, because I copied and pasted the whole thing, most importantly, I copied and pasted the pins, the input pins and also the output pin. So when I right-click and edit circuit appearance, the locations of the pins will be the same as the K3 circuit. So this way, I don't have to think about, oh, did I move the pins around, with this particular subcircuit? So we'll still have G, P, and K0 the same way as K3. So when we edit circuit appearance, somebody asked the question of what is this little notch here? Does anyone know? You have to be kind of about my age to really understand that part. But does anyone do you guys want to give it a shot? Like, guess why, there's a little notch? And I'm referring to this little notch here. What is the purpose of that notch? Why is it here? I mean, you're not bothered that there's a random notch on in a rectangle. Okay, that's the T part of a personality type talking. The third letter of a personality type, according to the MBTI, is either a T or an F.
I'm not really bothered, but what is it?
Well, things that cannot be explained, bothers me. Okay, because it's like, why is it here? Why is it like a notch? It doesn't do a single thing. So why is it here? Okay, it's here because in the good old days, you have chips that are usually hand soldered. Okay, so you have a person who's going to insert the chip and then they solder it. And most chips are rectangular. So without a visual clue, you can solder a chip 180 degrees rotated without knowing it. So the notch is actually a orientation aid to help people know which way is that direction. Yep. So if you go to Fry's and you buy, some of the kind of like the bigger chips, and you observe carefully, there's actually an indentation. So this is not actually just painted on the chip. This is actually a plastic indentation on the chip packaging itself, to basically remind people which end is pin 1, because the pin numbering. Okay, I cannot be 100% sure, but I think pin 1 is this one. So it goes like pin 1, 2, 3, and then 4, 5, 6, like that. So basically, this notch helps people identify which side is pin 1. Because if you solder certain chips, 180 degrees rotated, bad things will happen. Very bad things will happen. You plug in the power, and then you'll see firework. You'll be letting the genies out of the chips. Genies, yep. Okay, so this is K2, and it is time to test K2. Go back to main. So we just have to wire up K2 the same way that we wire up K3. Okay. So we just have to say, okay, let's put G into here too, let's put P into here too, and let's put K0 into here as well. All right, so is it working correctly as we speak right now? Is K2 supposed to be a 1 based on the input pins? We are basically adding 0, 0, 0 to 1, 1, 1 with an input carry of 1. So would that trigger K2 to become a 1? Zero, zero, zero. Okay. So we are dealing with 0, 0, 0 plus 1, 1, 1. But we also have a carry of 1 as the least significant carry. So 0 plus 1 is a 1. 1 plus 1 is a 0 with a carry of 1. But this is K1. We are not up to K2 yet. 0 plus 1 is a 1. 1 plus 1 is a 0 with a 1. This is our K2. So K2 being a 1 is actually correct. 0 plus 1 is a 1, 1 plus 1 is a 0 with an overall carry. So that's K3. So we can see that K3 is a 1, K2 is also a 1, so the circuit is working correctly at this point. All right, so one more. K1 is the easiest one. So we'll do the same trick and just copy and paste. Copy and paste. This is K1. And we remove all the wiring. I keep the splitters even though I don't need it to split three-way, just because, hey, you know, it just makes the circuit look a little bit uglier, but it doesn't make it incorrect. So we know that we don't need the 3-input AND gate anymore. The OR gate goes from 3 input to 2 input. And I know the documentation basically says, you know, you don't need to do this. Okay. Yeah, it looks ugly. And then the equation says K1 is G0 plus P0 K0. So G0 goes straight in. So this is G0, it goes straight in. So that means I have to remove this wire and reconnect this one to one of the inputs of the OR. And then the AND is between P0 and K0. Alright, so we get this guy. Get rid of this. So I can connect here. Not the prettiest, but I think it's right. And then we adjust that to K1. And edit appearance. The wrong thing. Okay. I personally like to label all the pins. Has anyone thought about, you know, now that we know how to do adders and subtractors and also how to compare, how do we make a multiplier or a divider? Has anyone thought about it? Yep.
I think there's an option in there that gives you an actual multiplier or divider. So you just go in there and
You mean go to arithmetics?
yeah.
Do they have a multiplier?
Yeah, it's right.
Oh. But if you're only given with adders and subtractors, do you know how to make it?
Like if you multiply by 2, you gotta add the thing.
Yep. Mm-hmm. Well, maybe that's one of the things I can talk about when we have time. Okay, so K1 should be wired up. And at this point, K1 should also be a 1 because of the way I set up these numbers. So that's okay, that's all correct. So now that we have all of this stuff here, I'm going to pull K0 into here, you know, just so that it's ready for the merger to merge into the K wire bundle. So we are almost done. This is already a merger, just copy and paste. So or duplicate and paste like this. The bit numbers are off entirely, so there are several ways to fix this. The way I'm going to fix this is just to reverse bit 0 to be the bottom one, and then bit 2 to be the top one. So yeah, that's the quickest and easiest way to do it. So wire this up. This one goes over here. And this one goes to the bottom. All right. So now we just have one more thing to do. We have to use an exclusive OR to exclusive OR the carry with the Q. So we just need to go to this one here because we got one already. So we just duplicate this. And wire it up. and then specify 2 output pins, and we are done. So one output pin is just the overall carry. The other one is the result of the computation. Which I'm going to call, it's really hard to call this one, let's just call it result. Alright, so let me zoom out so we can actually look at the calculation, and we can just test it. So how do you guys want to test this circuit? We can do addition or subtraction. Okay, so this is a test already because I'm specifying that we are subtracting 0 from 0 with a borrow in as 0, and the result is 0 with no overall borrow. Makes sense, right? So we can now test the next one, 0 minus 1. 0 minus 1 should give us 1, 1, 1 as the result with an overall borrow. So we just specify a 1 over here, and we do get 1, 1, 1 as the result with an overall borrow. Does it make sense from the signed perspective and also from the unsigned perspective? From the signed perspective, 0 means 0, 0, 0, 1 means 1, 0 minus 1 is supposed to be negative 1. Is 1, 1, 1 representing negative 1? Yep, so we're good. From the unsigned perspective, does it make sense? 0 means 0, 0, 0, 1 means 1, 0 minus 1 is giving us 7 with an overall borrow of 1. What are we borrowing? What is the quantity that we are borrowing? We're borrowing 8. So that makes sense as well, because you have 7, but you owe 8, so the actual quantity is negative 1. Okay, so let's try something that will have a carry. So let's flip the subtraction to addition, because that's one of the nice thing about this circuit is I can change one bit, and it goes from a subtractor to an adder. So we are now adding. Is the result correct? I'm adding 0, 0, 0 to 0, 0, 1 with a carry in of 0, and then the output is 0, 0, 1 with no overall carry. That seems right. And let's try this one. We are adding 1 to 1. The result is 0, 1, 0 with no overall borrow. Seems right. And then we flip the flag, so we turn this back into a subtractor. 1 minus 1 is 0 with no overall borrow. That works too. So that's kind of a neat design in a way, because you're basically reusing the same kind of circuitry, except we are just adding this one extra thing to the entire circuit, so that now it can do both addition and subtraction. So in the spirit of RISC computers, this is actually helping to make the chip use fewer transistors. I think in this class we talked about 4 gamers in a room, and each one has a 1 kilowatt gaming computer. Yep. I think we did talk about that. So the other day I was showing the class this. Okay, it's Apple II Strike Eagle, and actually it's a different class, but nonetheless it is kind of interesting. This is a flight simulation game, of the F-15 Strike Eagle, and the game is from 1985. Okay, so this is from 1985, and this is the best. This is the state of the art back in those days in flight simulation. And of course, by today's standard, you guys would go like, my watch can do this, right? At 20 times the speed. But you have to remember what kind of processing power is available back in those days. So how do you figure out the approximate amount of processing power just based on time? Moore's law? Okay, what is Moore's law? Moore's law has to do with, okay, so let me switch to the tablet. We don't get to appreciate technology or how far we have gotten along because we don't usually look back, right? So now that we have looked back a little bit, what is Moore's law? Moore's law is a very interesting equation. It basically says, processing power. It doesn't say that. It says transistor density doubles every 18 months, okay? Which loosely translates to doubling the speed every 18 months, okay? All right, so the question now is how many 18 months has passed since 1985? Well, give me a rough number, just a rough number here, okay? This is 2018 minus 1985, so we are talking about, what, 33 years, okay? So 33 is a good number because, every 3 years there are two 18-month cycles, right? So, so every 3 years there are two.
22, I would guess 22.
So we have to divide it by 1.5, and that gets us what? 40. Is it 1.5? 18 months? Yeah, 22. Okay. So we have gone through 22 18-month cycles. Okay, then you look at this number, go like, so you mean that Apple II computer is about 20th the time, or the about 5% of the processing power that we have today? No, it's about 1 over 2 to the power of 22 of the amount of processing power that we have. So in other words, we are looking at this number, which is about what? What is the quickest way to figure out what is the approximate amount of 2 to the power of 22? 2 to the power of 10 is about 1,000. So this is approximately 1,000 times 1,000, which has 2 to the power of 2 left, which accounts for 4, right? So this is about 4 million. So we are looking at a computer that has the processing power of about this much of the PC that you have today.
I mean, that's considering if we have the PC state of the art today.
I don't know whether that computer was considered, state of the art even back in those days. But for the same amount of money, this is what you bought back in those days. Mm-hmm. Okay, so now the question is, okay, so is this number making any sense? Okay, so let's figure out let's look at the specs of the whole thing. So let's say you're buying a regular desktop computer, because that one is actually a quote-unquote desktop computer. What is an i7 processor? What is the clock speed? You guys don't put computers together anymore?
i7?
Huh?
i7?
Yeah.
Like 300?
So 3 gigahertz. I'm asking the clock speed.
i7 sits around like 3.7 to 4.0.
Okay.
Stock, I think.
Okay, let's pick 4. Okay, so without overclocking is 4 gigahertz. That's the clock speed versus 1 megahertz. The 6502 processor back in those days in 85 is only running at 1 megahertz. 1 giga is 1,000 mega. So right off the bat, we have a 1,000 factor already. What kind of what is the width of the i7 processor? In terms of 32-bit, 64-bit processor, what is it? 64-bit. Okay, so we have 64-bit processor versus 8-bit processor. So we have another factor of 8 here. Okay. How many cores do we have in an i7 processor, desktop version? Quad core is standard these days, right? Okay. So 4 cores versus 1. Another factor of 4. How many ALUs do we have in an i7 processor? Arithmetic logic unit. just for integers. I don't even care about the floating point part. Let's call it 2, okay? Which is total underestimating. 2 versus 1. Okay. Let's see what else are we going to compare. Number of cycles per instruction. Okay. In other words, how many clocks do we need to execute one single instruction for a single core? Okay. So I'm not double counting the multi-core factor here. These days with the i7 processor, most instructions that actually do any type of computation is about 1 clock to 2 clocks per instruction. So let's call that 2. Back in those days, we're counting at least 5 or 6. So that means we have to reverse it. So this is 6, this is 2, because we're counting the length of time. You know, if I do it the other way, this is looking at performance. So if you just look at these numbers, what do we get? So 3 times 2 is 12. 12 times 4 is 24. 24 times 8, about 200-ish, right?
180.
180.
184.
Yeah, 184.
And then times 4,000. So we are not quite at that point yet, but that's not taking caching into consideration. It's not taking DDR, memory technology into consideration. So when you add up everything that will give your computer, the performance that you have, I would say this number is probably actually realistic. So what does this have to do with RISC versus CISC? The 6502 processor is really simple. It is truly reduced instruction set computer. And why do you think it is a RISC processor? We are almost running out of time, but this is kind of important. So why do you think the 6502 processor back in 1985 that the Apple II computer used as the main processor, why do you think it's a RISC processor? What was our discussion again that we talked about why RISC is better than CISC? The gamer situation, heat dissipation, right? Do you think that was the issue back in 1985?
Oh yeah.
That was a part of the issue, but for the most part, that was not the reason. They simply did not have the technology to pack transistors the way that we can. So the 6502 processor, okay, let me show you the dimension, a picture of the actual 6502 processor. So 6502 processor. This is, come on. It's actually pretty big. Okay, so if you look at this is a picture of the chip itself, and the pins are spaced out at 100 mil per between the pins. So that's 1/10 of an inch. So if you count the number of pins minus 1, that will be kind of the length of the chip itself. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this chip is about 2 inches long by maybe about maybe 3.3 to 0.4 inches wide. That's pretty big as a package. So now we ask about, okay, what is the transistor size of that particular chip? Okay. Okay, so this chip has somewhere between 3,500 to 44,000 transistors. What do you think is the transistor count in the i7 processor? I would probably say it's close to 10 million. I could be wrong. Okay, so let's check that out. i7 transistor count. There we go. Oh, I was way off. I was way off. The i7 processor quad core has 731 million transistors, as opposed to about 4,000 transistors. So when you take all of these things into consideration, what was the reason why the 6502 processor was a RISC processor?
Simplicity.
They simply did not have the technology to pack transistors into chips. That was it. So is this kind of putting things into perspective? More or less. No, nobody seems to be interested. I mean, 4,000 versus 700 something million. So if you do some rounding, so let's call this 800 million. So what is 800 million divided by 4,000? Come on. 20,000, right? 20,000. So you can just kind of imagine that you can pack, just transistor-wise, you're packing 20,000 6502s into one i7 processor. That is a lot. Because 20,000, what is the square root of 20,000?
Maybe like half of square. It's 20 would give you 40.
What I'm trying to do is to try to come up with a visual. Huh?
About 141.5-ish.
141. Okay, so you can kind of imagine an array of 140 chips this way and 140 chips this way. That is the area of the packaging or the chips, and you're now saying, okay, you mean all of those things is now fitting into about this big? That is how far we have gone. Without that, what do you think we're going to have now? Do you think we have drones and autonomous vehicles and stuff like that? The computation power that you need for any autonomous vehicle will require several rigs, like 18-wheelers, to carry. That is your self-driving car. You can have a self-driving train, because only a diesel train can carry that much computation power and generate the power that is needed to run the whole thing.
But wouldn't it need less power because it's on a track, so it doesn't have to really guide itself?
I know, exactly, that's the point. But what about aerial drones?
That's a lot.
You have to have B7.
You have those transport planes or the B-52s. You have B-52s tethered for communication, and a whole bunch of refueling airplanes to keep them in air. Yep, there's your self-flying drone there. Yep, and you need a license to fly that thing too. If you can afford the fuel, let's not even think about the actual hardware on that thing. Even if we can afford the fuel, that's the funny. That is how far we have gone. Yep. Question?
Look on the look real quick and look at the one with the most transistors.
Look at what?
Click on the processor with the most transistor count. Yeah. No, just click on.
Oh, just right there?
Yeah.
The blue one, the blue
Transistor count.
Yeah.
transistor count.
Yeah.
Oh, okay.
Scroll all the way down.
Scroll down.
Is that the one? Wait.
There was a graph up there.
Well, the graph doesn't. Okay, let's see what kind of resolution are we getting out of the graph.
No, the graph doesn't do it.
Well, the graph shows that the highest million in
That
terms
was
of count
2011 though.
is a Spark T3, a 16-core Spark T3. But the 6-core i7 is pretty up there too. That is already exceeding 1 billion transistors.
32-core AMD is 19 billion right now, 2017.
19 billion?
About 5.5 times.
I don't know. That doesn't seem.
It says 2011 right
That's
there.
2011.
Oh, okay, so that's outdated. Okay, that is interesting.
That's like.
Well, but that's Moore's law. That's Moore's law talking right now. Just between 2011 and 2018, how many 18 months has gone by?
Between 11 and now.
Yeah, let's call it 6 years. Okay, if we call it 6 years, You divide it, so 4 cycles, right? So 8 times. So we are looking at this graph and saying, okay, times 8, that will be the current standard. Is that pretty close? 19 million versus 19 billions versus 2 billions. So Moore's law is still at work. Despite people saying, no, we have hit the limit, that cannot go any further. It's still going. So this can only help you kind of think about the future. Like drones being microscopic, it's already getting there. Yep.
So I've been hearing about quantum state transistors. Is that basically, if we get to that point, is that basically what's going to happen? It's just going to keep, things are going to get smaller and smaller?
No, the quantum stuff is different. You mean a qubit? Q-U-B-I-T?
I've just been kind of hearing it between classes.
No, the quantum computers are actually pretty big because the components to detect a state change or the spin change is not small at all. The power of a quantum computer is it can explore multiple possibilities at the same time. But we also have the difficulty of observing and find out exactly what state it is in because it's not exactly in a particular state. So quantum computer would take computing to the next level, but in a whole different way compared to just miniaturization. So that's going to be a really, really interesting thing when we get to quantum computing. You guys may actually get to quantum computing in your career. Because there's no telling whether 20, 30 years, in 20 years or 30 years, we can get to that or not. Yep.
How far are we from that? I'm saying if things keep doubling, how far are we from getting down to the size of atoms?
Well, there are certain things we cannot, certain boundaries we cannot cross. Okay, remember now we are just completely out of context now, so if you need to go home, go home. So remember the transistor looks like this, in the schematic. This part here is an insulator, okay? It is the metal oxide that is actually forming an insulator, so that this plate and this plate they're actually separated. The transistors that we have are so small that this barrier is so thin that electrons can jump across. The quantum effect of transistors is already jumping across this barrier, which means we cannot make transistors any smaller than what we have, or at least in terms of magnitude, it cannot be much smaller. Because any smaller, if this barrier is any thinner, then this plate, which is our gate, and the substrate is no longer separated. And field effect transistors cannot work without the insulator in between. So we are already, small enough where quantum mechanics is already, interfering with the operation of transistors. So we cannot go smaller than a certain level. So we have to change the nature of computing altogether in order to take it to the next level. So very interesting questions. All right. So I'll see you guys next Tuesday. If you study and you find out there are certain things that you want me to go over on next week before the exam, bring those questions. That's the whole idea of the review.